So let me just quickly uh, emphasize or remind ourselves what we were after. So where we stopped, without worrying now about the first few classes, let me just finish this and then I'll remind you where we were. So what we are trying to explain as far as the theory for turbulence is concerned is the following. We had seen that when we looked at this object, which is taking the pth power of the velocity difference between any 2 points at x and x plus r, and take the pth power, some sort of scale invariance or cell similarity sort of suggested that you had this going as a power r to the power something, where the label p just says that I'm going to take the pth power. All right? And we saw that if you use Kolmogorov theory or simple sort of cascade picture phenomenologically, all of them led us down the garden path to this exponent being equal to p by 3. But as I told you, and today I'll just show the data, just not my own sketches, but this is all data. There's more improved data. What you will see if you, this doesn't, okay, now it's working. So what you see, these points are the points that you should kind of trust. This is data from some years ago. And what you see is this p by 3 line of Kolmogorov is certainly not compatible with the actual data that you're going to measure from, let's say, a wind tunnel or sending a balloon up in the atmosphere or going down to the depths of the ocean where the flows are turbulent, or putting a little sort of measuring device inside your washing machine when it's going full tilt. So any sort of turbulent measurements that you can make, as long as you're far from boundaries, so you're within the overall assumptions that we've used in all of these lectures, within statistical homogeneity and statistical isotropy, you end up with points which sort of look like the scatter, if you follow my sort of pointer, the scatter that you get there. And that certainly sort of shows that p by 3, which we got from different arguments, is not quite correct. However, we know that whatever we need to do, and you can see here, all the points are bang on when p is equal to 3. And as I mentioned several times, the fact that the third order exponent is 1 is not an outcome of anything. It's consistent with the phenomenological pictures that we have been developing on the Kolmogorov theory, but this you can prove independent of all of that directly from the Navier-Stokes equation. That's the only thing that you can prove. The other sort of thing that we touched upon is this experimental fact. I should have brought a picture for that, but maybe I'll show it to you all tomorrow. Is the experimental fact that the dissipation rate does not seem to vanish as viscosity goes to 0. And this, all of us sort of feel it in our bones that something much more mysterious is going on than intuition or anything else would suggest. All right, so I should have also written this here. So the fact that there is a curvature from p by 3, and the fact that it seems to show more than one scaling regime, because that's the only way we can explain things. If something, second order or fourth order doesn't seem to be trivially related to each other. Otherwise, the fourth order exponent should have just been twice the second order exponent. All of this seems to suggest that there might be several different scaling exponents in the system, and depending on which order you're measuring, you're sampling one or the other. So that is an idea whose time had come, and we had sort of taken a digression in the previous lecture and looked at the simpler 1D Burgers model which doesn't have a lot to do with turbulence, certainly in the way that we looked at it in the previous class. But what the Burgers model showed us was an analytical way in which we can see the fact that there could be multiple scaling exponents. Remember, it was a bi-scaling regime. It wasn't a straight line versus P. And the fact that the viscous dissipation in the limit of viscosity going to 0 converged to the dissipation that we found very surprisingly when we began our calculations by explicitly taking the coefficient of kinematic viscosity to be equal to 0. So in order to return to the turbulence problem, we decided that since the phenomenology that we had developed to get P by 3, both Kolmogorov and in the sense of pictures, gave us at least things which were sort of valid till P by 3, and certainly it sort of enforces the zeta 3 equal to 1 constraint. We sort of said, all right, let's build a model where I'm going to sort of tinker around with this cascade picture, because I know again from data, we had looked at it, the fact that things are intermittent. So why not try to make our cascade model, quote unquote, intermittent? And the simple way that we sort of constructed this argument in the last class was to actually look at that model, and within the inertial range of scales, so each scale of them trivially corresponds to some factor A, which I don't really care about. It's bounded between 0 and 1. 1 would be there's no cascade. So each of these scales correspond to the nth generation corresponds to some A to the power n into L, L being the largest scale in the problem, till it goes all the way to viscosity. And here all action happens, because this is where there is an energy dissipation. This is where there's an energy injection. I think I used I. And this is where there is good old flux pi. So, and this is an idea which was confirmed when we sort of looked at the conservation laws from the Navier-Stokes equation, which seem to suggest instationarity in this multi-scale problem that we got introduced in the first lecture. You certainly have I on average, I is equal to pi is equal to epsilon, all right, for stationarity to be maintained. So I won't go through again the details of the calculations, but just to remind you once again that when we put in this factor, and remember this sort of gave rise to some factor phi at the nth generation, which will give me the fraction of stuff which is active. When the dust settled, we sort of found an expression for the same scaling exponent, which is pure Kolmogorov, P by 3, but with a correction which depends on the dimension D on which my cascade is accumulating. So essentially, there is a process of flow of energy from large scales to small scales. It is in a three-dimensional embedding space, but the structures on which this transfer of energy is happening, that is in some other dimension D that we don't know or care about right now, but it comes out of erasing some of those objects, which I've just colored with pink, and then you end up with this expression. The good thing about this expression for self-consistency is when I take D equal to 3, which is the Kolmogorov picture where everything is nice and smooth and regular, all of these sort of, all these generations are alive and kicking, then you end up, this factor disappears, and so you just get the good old P by 3 scaling. The other sort of advantage that we had was the fact that for P equal to 3, you again end up exactly with zeta 3 equal to 1. So there is self-consistency in what we did. All right, so this was just a quick reminder. And remember, we ended the last class by saying, so I just wanted to show you that, and then I'll get rid of the slide up there, that it turns out that, and this is something you all can play with because now you have the values of these exponents from numerical data or experiments, and you can do your best fit that you can that you want to do on GNU plot or whatever software you guys use, probably Python. And if you take D to be 2.8, this was in the 80s when people sort of started worrying about this problem. So here is a line that you see right there. And that line essentially is this function, but where D was taken to be 2.8. And as I mentioned in the previous class, that let's say up to around these range of values, it does seem to do a reasonable job. But of course, this cannot be the answer to our problems, right? Because even within the beta model, this formula will again give you a straight line. It's a straight line which is different from the p/3 line. It has a different slope, all right, but it certainly cannot give something which bends away. But up to lower order moments, maybe it does a reasonable job. If you did not know any theory and your friends gave you the first 3 or 4 or 5 of these numbers and you sort of did a least fit which fits that data so that things are spread equally on either side of that line, then probably this formula gives you a reasonable agreement. So yeah.
Just a coincidence, or there is something?
Sorry, the fact that this agreement?
Yeah.
So it's somehow built in the algebra that we did. And so all it says is the fact that zeta 3 is equal to 1 was already built in from this self-consistency. So maybe I'll just take 1 second to do it. So remind ourselves. So you remember we can calculate the flux at some scale R as the kinetic energy on that scale divided by somewhat the local turnover time. So this animal will give me VR cube over R. I'm just not worrying about the normalizations, etc. So we know that this will be the same as epsilon because of this constraint. So this whole thing cannot depend on scale per se. And that essentially tells me that VR cube will go as R to the power 1. All right. So when I play this game, then all I'm doing is I'm having additional factors here, which are somewhat probabilistic of how I'm getting rid of some of these intermediate structures, but this set still holds. So I won't go through the algebra that I did in the last class, but basically this will be decorated by factors which seem to show up in this combination.
Whatever material you choose, this will be always.
Right? This will be, yeah, right? It's built into, so this is really built into the notion of stationarity. Exactly. Okay, good. So let me get rid of this now and proceed. No, these are just measurement uncertainties in the 70s and 80s. Right now, if you look at current data, I mean, no one measures these things anymore, but from the mid-90s, 2000s, the data have very well settled into. So in case you want to know, for example, what the values of these exponents are, off the top of my head, you can find it in 2 references. One is a paper by Benzi et al. On extended cell similarity. In 1990, I don't remember the year, but before 95. All right. So there you'll get the list of what is the value of zeta 1, what is the value of zeta 2, etc., from real data. And from an analogous sort of toy model, which we may or may not do in this lecture, there is another paper which lists it very well by Mitra and Pandit. This is PRL 2004, which also lists the value of these exponents from p equal to 1 to 6. And you can have fun sort of fitting this formula to those sort of data and you'll see you're running into trouble because you're trying to fit something which is curved with something which is essentially straight line. So there are sort of small regions that you can fit. After all, something which is curved, you can take a small section and. Okay. Very good. So what we'll do is, as all of you suggested, at the end. Okay, quickly. Any questions on this? No. Oh, okay. So what many of you suggested in the last class is that we should be able to massage this model a little more to make our formula start bending. Right? At the end of the day, our job is like, like this sort of weightlifters who are trying to sort of take this straight line and the beam and trying to bend it so that the curve becomes concave. So the first extension that we can think of logically is what some of you suggested. What happens if I take two values of d? There is nothing which tells me that the cascade, I'm just sort of simplifying the picture a little bit, but in terms of sort of measure theory, you should think about it slightly more cleverly. But there is nothing which prevents me from saying that I have several such cascades going on, and each of them might have a different dimension d, and hence a different scaling exponent h. Right? Several is a large number, which I do not know of. So first, let's assume that there are two of them, and then see if we can get somewhere. So if we take two of them using the same ideas, we can think of one set S1, which corresponds to one dimension D1, which corresponds to one scaling exponent H1. Here, everything was only one, all right? And we can think of another set S2 corresponding to some D2 corresponding to some H2. Right? Where both S1 and S2 belong to the base. So I'm somewhere here at point x1. I'm somewhere here, let's say at point x2. And I understand that the cascade, this tree that's happening here, is somewhat starting around x1, where it all accumulates on some set of dimension d1, and the associated scaling exponent h1, which I can get from here. And the other animal correspondingly accumulates on some d2, on some set s2 with some d2. All right. So if you remember from the last class, now I will be a little more careful with my notations. So I will write it in the non-dimensional form. So then, in principle, I will have this goes as some h1, this go as some h2, if x belongs to set 1, or if x belongs to. Right. So suppose I was calculating the velocity difference standing here. R is the distance between Sanjib and me. Then I probably converge, or the cascade accumulates on set S1 with corresponding dimensions of these structures as D1 and scaling exponent H1. But suppose I'm at X here with the same separation between you and me, then the corresponding cascade is accumulating on another set S2 with dimension D2 and corresponding scaling exponent H2. All right, so this is a first extension. It would be what would be called a bifractal model. You can see the word bi here is for the it's due to the fact that I have chosen two options. So what this means is, if I look at the pth order structure function. Right? Where these are some order one constants that I really don't care about. It's telling me how much weight, if you like, is there on, sorry, on my measurements as I move from X at different X's, right? After all, I will eventually be taking averages, so I'll be averaging over X. All right? So this essentially is a superposition of two power laws. And we've already seen what to do when we have a superposition of two power laws, right? If the world was exactly what we have here, and I were to take log-log plots of R here and some SP here, at the end of the day, whatever your favorite software would be, you'd probably convince yourself that there is some straight line. Maybe it's noisy, but you will fit one straight line and you will get one exponent up to the power zeta, right? So if there's a superposition of these two exponents, because R is going to be, R over L is going to be a small number, we did this yesterday for the Burger's equation. Remember, the Burger's equation, the structure function had two terms. One was R to the power P, which came from the smooth part of the solution. The other was order R, which just came from the probability of having the jump discontinuity. So we'll play the same game. And what you're going to measure in your experiment in a fictitious world where everything is bifractal in the following way, what you would end up getting is the measurement that you'll make will be the minimum between pH1 plus 3 minus T1 and pH2. Yes, we will. Yes. So we will then make 3Ds, 4Ds, 5Ds, but that will be extremely boring and tedious. I have to keep on writing things. So from 1, 2, we will jump straight to infinite. Because, you know, after 2 comes infinite. All right, that's what we'll do, yes. But jumping from 1 to infinity might be a bigger jump. So let's do it at least 1 to 2, but you can do 3, 4, 5, however many you want. All right, so when you do that, you end up with this. So what does this tell us? So let's see if we have been able to bend our curve just a little more, right? And so what we can do is, let's use an example of this. At this stage, I should warn you, don't take the syllabus anymore, which is on the website, too seriously, because I don't think we'll get there by tomorrow, end of class. Okay, so what we'll do, yes. Yes. No, because it just comes from just the algebra, yeah? What you're right, what will happen is, and that's always going to happen, in actual measurements, all right? Remember on the first day I told you all to be nice, compassionate, kind, and show empathy for your friends who work on these problems. So what will happen is that, you know, in reality, you will never have R over L going to 0. It'll be sort of finite. And these two exponents might be pretty close to each other. All right. So then the fact that one dominates the other, think about x squared plus x cubed, where x is small. It has to be really small so that in the data you'll just see x squared dominating. Otherwise, what you'll end up seeing is something which is somewhat curved. Maybe your data might be more like this. And then your friends will say, okay, this fit works. All right. Okay, and that hopefully will be the min of this. Okay. So let's take one example. So the first example that we can think of is the following. We can say, all right, Kolmogorov did tell us that that's going to happen. Depending on your point of view, you can say that Kolmogorov was wrong just by a little bit, or you can say, the idea itself is not completely consistent with what we understand about turbulence. So you can ask the following question and say that, all right, maybe one of these dimensions could be what Kolmogorov had in mind. So maybe I can take, So maybe you can say that I probably can have one of these dimensions as 3. That's the Kolmogorov picture, which corresponds to h equal to 1/3. And you can argue, all right, if this is the room in which you're making measurements, let's say and each of you are sitting at point X, let's say for most of you, it actually doesn't matter whether it's most or less or what, but for some fraction of you points there, your neighborhood is kind of Kolmogorov-like. I mean, after all, Kolmogorov gets very close, so there's no reason to doubt that nothing of that exists in a real system. So that would mean that one of these d's would be 3, and the corresponding exponent will be 1/3. And let's say the other guy will be some d. It could be what the beta model fits us, where we took d to be 2.8, with some corresponding exponent, which I'll just write down as, is it 1/3? Yeah, what's the devilish game I'm playing? Mu's are order 1 constants. I really don't have to worry about it too much. So now I can calculate what my exponents would be, and then I find my exponents to be quite interesting. What I find is that the exponent for p less than equal to 3, the exponent is dominated by p by 3, and for p greater than equal to 3, the exponent will be I've just taken the min and I've replaced all those p's and d's with whatever I want. So here I've taken this to be 1/3, this to be 3, so there's no term here. So I'm essentially taking the minimum of p by 3 and, where's my h there? And p into this plus 3 minus d2. And I'll see that when p is greater than equal to 3, this guy will dominate. When p is less than equal to 3, the other guy will dominate. And if you plot this, then what you'll end up getting where this is the p by 3 line, and the other follows this expression. So we are slowly getting there. We've now, just by introducing a second dimension in the problem, we've actually moved away from a linear zeta p versus p plot, which is what we wanted to do all the time. By introducing a second dimension, we've actually started getting things which look like multi-scaling. Yes. This. You get the idea, right? Excellent. So as you were saying, if I start putting in more D's with different H's, etc., I might start bending things. Again, the beautiful thing is that at p equal to 3, the coincidence happens. And actually, if you look at the plot of here, I'm going to cheat a little, of course, because I'm going to plot data by hand and not by actual data. So if you remember, maybe I can give you some numbers from memory. So zeta 1, the number turns out to be 0.37, perhaps. Don't take them too seriously, but this is, I think, what happens. If there are any turbulent students in the audience, feel free to correct me. Maybe 1.52. This is sort of 1.83. Ballpark. One of you can Google and check. But what I wanted to say was that even with real measurements, you see up to p equal to 3, if you showed this to be p by 3, so this is very close to 0.33. This is very close to 0.67. This, of course, is 1. So even by introducing 2 dimensions, we are doing a reasonable job in fitting this part, and we might be doing a reasonable job in fitting somewhat this part. Right? Not really, but a reasonable job. So it certainly gives us some confidence that this might be a way to think about the problem. Let's think about another example that we did in the previous class, which was the Burger's equation, which certainly shows biscaling. So in the Burger's equation, what dimensions did we have? So the Burgers had this solution, right? So we would have one dimension coming from here. This is just a line. So D1 would be 1. All right. H would be 1 or 0. 1 or 0? Okay, let's fix dimensions. The shock will be a point structure with dimension 0, because we will work with isolated shocks. So the dimension here, remember, we calculate the velocity difference between 2 points on a straight line. It went as r to the power 1, right? So h will be 1. We calculated the velocity difference here, which went as r to the power 0, because the difference would be just the jump, right? I calculate the velocity difference between, let's say, this point and this point. I really don't care about r anymore, because it will be dominated by this big fat jump that I'm going to encounter. So this is going to be 0. So I can put it all in there, and there I will see, maybe I'll write Burgers with I'm in and we see that our phenomenological model that we constructed reproduces exactly the Burger's result. because by definition, the Burgers admits 2 dimensions and 2 scaling exponents, right? So again, this is a sanity check because that that graph you had already seen yesterday from real calculations on the Burgers solution, but now you see that this model gives me exactly the same thing. So the idea, as our friend was telling us here, was that if I continue to add dimensions, maybe I can take this guy and start to make it bend, 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 and have things which look completely concave. So this is, so let me just erase everything first. So first extension, now we will do second extension. Like MetroWorks, phase 1 was done, phase 2 is done, so we will do now phase 3. So what we need to do is, taking inspiration from the bifractal model, generalize the beta model to its continuous version. And this was an idea which was constructed by Frisch and Parisi. Actually, we haven't done too badly. We began in 1756 on Monday, and we are already in the second half of the 20th century by Thursday. Nice. Okay, good. So, but before that, I'll take a pause because this will now appear very, I will sort of mellow it down and wave my hands and write down certain things. But before that, I just want to take a 2-minute or half a minute break and just ask, is the idea of this cascade picture with all its sort of deficiencies reasonably understood at some level? Yeah. I'll just assume you nodding your head as representative of the room. So, yes, but now is the time to speak or forever hold your peace with what we are doing. Okay, fine. So just to recap why such a continuous version is even permissible, you will recall that in lecture 1, when we had looked at the symmetries of the Navier-Stokes in the limit of viscosity going to 0 or in the Euler equation, the Navier-Stokes permitted an infinite scaling group H. All right. Unlike the strongly viscous one, where you are pegged to H equal to -1. And from there, this was reduced by Kolmogorov to say that H can be 1/3 and 1/3 alone. Then the beta model allowed me an H, which depended on some fractal dimension, which entered my system because of all the sort of skullduggery that I was going on in the blackboard. And then the bifractal model allowed me the use of two values of H, two values of D, which is completely consistent with what Navier-Stokes would allow me. So I haven't broken any constraints that the Navier-Stokes had on me. And furthermore, in this construction, I've always been faithful to Monin, to Howarth, and to Mr. Carman by always ensuring that zeta 3 is equal to 1. Right? So I haven't done something very, very evil yet. So in this extremely beautiful piece of work by Frisch and Parisi, what they essentially assumed is a local scale invariance which you can contrast with the idea of global scale invariance implicit in Kolmogorov. And so the local scale invariance argument of Frisch and Parisi allows me to have an H, which I can change at will. So it's like a little slider or a knob that I can keep on turning. And associated with each of them is some fractal dimension D of H. And all these, erased it. And all the stylized S's that I had written, the set of fractal dimension D with their exponent H on which my cascade accumulates, etc. All those sets can also now come up with some label S of H. So essentially, the multifractal idea assumes the following, that you will have a set of an H minimum and an H maximum. This, for the bifractal picture, reduces to, let's say, in this case, the H minimum being 0 and the H maximum being 1 of scaling exponents. And then for every H that you find here, there which belongs to the real domain with so if I take the multifractal and reduce it to the bifractal, if I reduce it to the beta model, it would mean that H min is equal to H max is equal to H. D of H is just one number. D, the set is just one set S. If it's a bifractal model, then H min is 1. In this case, H min will be 0. H max will be 1, associated with dimension 0 and 1 on set S1 and S2. Right? So with this, we just generalize what we had written before in a reasonably sort of simple manner and write goes as R by L to the power 8, which we had done in the past, where X belongs to. This is exactly what we had written for the beta model, where I didn't need to worry about this part. This is exactly what I had written for the bifractal model, but there I had written two of these, H1 and H2, and I said X can belong to either of those. But now I have a continuous version of this. So when I write it down, I say that it will scale with H if and only if X belongs to the set S of H. And now, not surprisingly, I can write the structure function SP of R. I'll just write it in dimensionless form. This will go as R by L right? This is what we had all the time. Now, if I have a continuous spectrum of my scaling exponents H, it's a little awkward to sum over all of them. So instead of summing over all of them, I will basically integrate over the whole distribution. So I will say, will be integrating over all the exponents and all the DFHs, etc. that we have. So this is the most general form of the beta model where I've allowed a full spectrum of all these exponents. So the rest becomes reasonably clear. And you can now take the large Reynolds number limit, where R over L will be a small number. So this continuum will be dominated by the exponent that you will get, which will be the minimum of these numbers. Mathematically, but don't worry about the notation. Mathematically, you essentially write that this will be the infimum of PH plus 3. So you loop over all H's. Suppose you have some numerical data, God knows from where people have told you these are the different values of H that I have. You calculate, and the D of H. You calculate PH plus 3 minus D of H painfully for each of those guys, and then you take the infimum on the H. Yeah. Okay. Very good. Well, at some point, I'll probably scan these notes and send it to all of you, maybe. So this has to be coupled. Now it's not obvious that the Kolmogorov sort of the third order exponent constraint has to be satisfied. It so happened that it will, but you can add this as a constraint that zeta for the third order in all the toy games that we are playing with the beta and bifractal model, we saw it emerge directly, but here it's not so obvious, at least not to me. So I'd rather write it as a constraint that you have, that this model must satisfy. Okay, so any questions?
Satisfy the Kolmogorov.
This is just to satisfy. You can play with this a little and you'll see that this takes us a little deeper into the mathematical sort of massaging of these arguments. But if you play a little with all of these ideas, you'll see that they not only satisfy the zeta 3 equal to 1 constraint, but all the sort of exact results on random functions which are intermittent that we had used earlier. Right? Sorry. This, it's some measure. So in the bifractal, I had the mu1, mu2, some order 1 constants. It's some measure that I don't care about. And in my, so from this sort of expansion, if I want to get the zeta p exponents out, I'd probably take a log, etc. And what you have for mu really doesn't matter. It's just the measure of the likelihood of you being on set SH. But in the exponent, it really doesn't matter. Just take the log, take R over L going to 0. That sort of drops out of the problem. Exactly the way we wrote in the bifractal model as mu1 R over L to the power blah plus mu2 R over L to the power blah 2. But when you calculate the exponent, it really doesn't play a role. Okay. Good. So now we see something, well, maybe we won't have a lot of time to see that, but let me alert you to the possibility, because it's just painful, that what you see is zeta p's and d of h, those of you who are familiar with those ideas, are related to each other by just a Legendre transformation. After all, you can move from d of h to zeta p and zeta p to d of h. They're just a Legendre transformation of from one to the other. Recall thermodynamics if you've sort of forgotten how to worry about it. But there is perhaps, I have time to just go through one more idea that comes out of the multifractal model, and it's the following. This is, so there's the original paper in 85, but the book by Frisch has also a very beautiful chapter on how to understand these things. So especially all the things that I won't be touching on, which has to do with what happens inertial range, dissipation range, in between ranges, etc. That's a very good reference for you to look at. So there is one other way in which we can see, I have this, but in the last lecture, the lecture before, we had convinced ourselves that zeta p versus p, the curve has to be concave. So there is one way we can, and that's not entirely obvious from the way that we've written this formula, right? So maybe there's one way we can sort of quickly see that, and that's the following. What I can do is I can plot, by the way, don't take this plot very seriously. That's because we really don't know what d of h is. In some cases, we don't even care. But let's assume there is some h minimum and some h maximum. Remember, I think I'd used I, the interval for h min. And so far, we really haven't discussed whether the minimum h minimum has to be 0, h minimum has to be minus 38.7, or h minimum has to be 42 or 1/3. So far, there has been no constraint on the h min and the h max. So let's assume there is an h min and an h max, and I'm not telling you where the origin of this graph is, so I'm being deliberately vague. Then we might have, shape really doesn't matter, we might have some d of h in the following fashion. So on the same graph, I can also start to draw some pH. Maybe I should have used a different color. And what you find from that formula is, if I look at where this is maximum, which corresponds to some h star of p, then this maximum will be 3 minus zeta p, right? The analogous plot, and that just comes from the fact that you have that relation of pH plus 3 minus zeta p. Now the maximum of this guy will be where the tangent line exists. So the maximum of this guy will be where the slope calculated at p will be exactly equal to. Right? Well, I've drawn a pH slope. The reason for drawing this pH comes from the fact that I have a factor of pH here. So the difference of that the maximum sign distance will certainly give me my 3 minus zeta p. Signed, that's because in principle I could have drawn this curve below this and this above this. It really doesn't matter. What matters is that at some h star p, this animal will have its maximum. So if I take the derivative there at h star p, the derivative with respect to h, then I will have, that will have a value of p. Now that's very interesting because it will help us in a couple of lines to prove the last thing we need to, well, there are many other things to show, but one of the things that we stressed on during the last few lectures, and it's the following. So with the two definitions in place, I can write p h star of p plus p minus d of h star. Right. To show concavity, I need to show that these will always be positive, right? It cannot go down. Yes, this can't happen. So it has to be positive. With this sort of geometrical way of doing the same thing, I can actually calculate d star d zeta p dp, and what I would get is p plus, here this goes out of the window, and so no, I could do the other way around. I could do h star of p, taking the dpd there, and then I have p minus but we know what this quantity is. This we'd already calculated from here. If you put that in there, you see that d zeta p by dp will be equal to h star p. And in general, if my h min is a positive number or 0, then the slope of zeta p versus p curve will never be negative, and it will always say, it will always stay concave. All right? So you can later worry about this, and to make things life simpler, you can go back to the bifractal model, and then you can see that this thing eventually, for the Burger's equation, for which you know every result, for p greater than 1, this derivative will actually turn out to be 0. Right? And your h star p will pick up the singular value. Okay. So that's one sort of easy way to think about this problem. And that's one way to sort of see that h min is certainly going to be something which is 0 or above. So I can actually now put my 0 somewhere there. And I can slide h min all the way to 0. You can play several games with this model and see that many of the things that we learned in the last few classes actually sort of hold, and some of them hold in very interesting ways. So for example, if you were to calculate the Kolmogorov scale now, remember it just went as L Reynolds to the power minus 1 over 1 plus h. Yeah. So it goes as minus 1 over 1 plus h. Now, the fact that you have an age variation means that at the end of the day, you have an eta min and an eta max corresponding to 1 plus h. So what that means in reality is that the length scale at which this dissipation starts to act, this length scale itself fluctuates. So if you take a drone and fly up in the atmosphere, where the clouds are, where the flow is turbulent, and you calculate the dissipative scale. Suppose there is a way to calculate the dissipative scale, then at different points in time or space, you'll get a different value. That's because the dissipative scale appears to be something which is going to be a constant because there's some length scale which you can take the large length scale. There's some Reynolds number which you can even hold fixed if you can do a controlled experiment. But the multifractal model guarantees that my H will fluctuate between a minimum and a maximum value, which in turn guarantees that my dissipative scale will also fluctuate. So essentially, if I'm thinking of this cascade picture in a completely sort of heuristic, cartoonish way, what I would have is this inertial range kind of go up and down, and the dissipative scale also fluctuating like mad. It doesn't fluctuate like really mad, but it does fluctuate quite a bit. Right? And so all these ideas of intermittency, etc., you see are wedded into this argument. That's because the scale at which you're dissipating, that itself is a fluctuating length scale. And the fact that that's a fluctuating length scale can sort of suggest ideas of why everything else which is constructed on those scales can also be nicely intermittent. Now, there are sort of very interesting questions which are quite involved, which has to do with how one interprets such models. So maybe I'll come back to some of those ideas tomorrow if I have time, but for the moment, we just satisfy ourselves that with that kind of picture, we eventually are able to break the not equal to p by 3 that we wanted. We are able to get a curve of zeta p versus p, which is continuous and concave, and which will satisfy everything that the experiments tell us. The only disappointment that I see in all of you is that you probably wanted at the end of this exercise a formula which will fit the data, right? We all want that. Unfortunately, there are no free lunches. And so essentially, this phenomenological model will not give you an exact formula, but you can use this, play around with the D of H's, and people have been doing that for years. And there's very fine work, which I'll come back tomorrow and discuss a little bit with you guys, which sort of tell you how well the multifractal model works in practice. The fact that you can scoop out these different Ds from different measurements and then sort of roll it all back in together and you get it. What you don't get from any of this is a quick fix formula that zeta p goes as p by 3 plus p squared over 9 plus whatever, right? There are other ways into which you fit it. There are other models, but this probably gives you the best sort of insight into the physics of the kind of fascinating multifractal physics that's going on. Okay. So we'll sort of, how should I say, take a break from this sort of picture and try and see if we get somewhat similar results, or at least partial results that we had with a completely different point of view. All right, so we sort of, while I erase it, it's like the intermission in a movie. So pause and ask me questions about how we constructed this, if not the algebra, but the spirit of it. And then I'll again go back to Navier-Stokes equation and try to find another path to come to similar results, and hopefully using techniques which hopefully might be of some use to some of you in the kind of physics that you're doing. I'll keep this. I don't. All good? Okay. So when we constructed these sort of cascade models, we had kind of divorced ourselves from the Navier-Stokes equation, right? We had sort of looked at the Navier-Stokes equation, taken a lot of inspiration from the conservation laws in the Navier-Stokes equation, from the fact that nonlinearity leads to redistribution of energies. We had used ideas of scale invariance, we had used ideas of locality of interactions, etc. But we really had sort of moved a little away from the Navier-Stokes itself. By the way, I just wanted to make one remark, which is this connects to what we were doing before, that within this class of cascade models that we did on the blackboard, there is a rather interesting and useful generalization, which is solve numerically. Solvable models. These go by the name of shell models. They're useful because unlike the Navier-Stokes, you can actually numerically solve them on your laptops in about half an hour, 40 minutes, and you can generate all those numbers that I was showing you. So maybe tomorrow, towards the end of my lecture, unless Ritik, did you do any of this in your tutorials? So maybe tomorrow at the end of my lecture, I might be able to cover this. All right. So let's try and see if some parts of these can be derived more systematically. This is the goal of this part of the class. Because we began with Navier-Stokes, right? At some point, I need to find my way home back to Navier-Stokes. So today and tomorrow, we'll try and find our way home back to Navier-Stokes. Okay. So what we will do is something that is routinely used in statistical physics. We will use a kind of coarse graining approach. Before we lay it out, let me make some definitions first. So what we will use a lot is a filter. I need to stick to the same notation, R, which is centered some R. I realize I'd used the letter phi also when doing the beta model just to define certain fraction of things alive. This has nothing to do with that. I just used it intermittently. All right. So essentially what a filter will do, maybe I'll just list its properties and then I'll sketch it out in a more intuitive way, is the following. So this filter, I will make sure that it has the following properties. It's positive. It goes to 0 as R goes to some large number, because I have to eventually worry about this a little bit. What this filter does might be something of this sort. Suppose you have a signal, some signal, don't even think about turbulence or whatever, some function. My phi, for example, could be like a little hat, which is centered here, let's say, at r equal to 0, right? So as you can see, you can't right now, we have drawn it. So as you can see, this function phi, which could be like a Mexican hat, a Gaussian, whatever, certainly goes to 0 pretty quickly from its center, which the center that I conveniently choose at r equal to 0. I've made sure that this is positive. You can even think of this as some velocity. It's positive, and I will normalize it such that the integral of this, the area under the curve, is going to be 1. And it's also kind of symmetric around r equal to 0, which is an intuitive way to see why the integral with respect to r, which I forgot to write here, has to also go to 0. All right? That's because the negative and the positive side will compensate each other. So what we'll do is we'll take recourse of this filter and try to see if we can get some slightly more concrete results. By the way, in this talk, in this part of this lecture, I will be using some inequalities which we don't need to prove. Those of you who want to prove, you can sort of go back and prove. These are kind of textbook inequalities. But if we understand the notation of those inequalities, the results follow kind of rather simply. All right. So now what we can do is we can introduce some length scale L in this filter. So introduce a length scale L such that I'm going to label by my filter with the label L. This will just be something which is L minus D phi of. You've seen many of these ideas in Sanjib and Abhishek lectures in the last week. Sorry. Yes. So this is just saying that if I integrate this guy with the R vector itself, then this will be 0 because things are symmetric on either side. Okay. R. Yeah, and this is the DD of R, so I'd forgotten to put the R in. Otherwise, this was the same as the one before. And I would have proved 1 is equal to 0, which might be nice, but may not be very useful. All right. So if I kind of apply this hat, so think about this like a hat. I drew it like a hat. So if I kind of apply this hat, what my filter will do is calculate the average. So let me first do it and then write it. So I can think about reconstructing this is the definition. So I have the velocity field V of x, all right? On that V of x, I've put in this filter, whose properties we've just described. So so this is my so this is my flow everywhere. I've taken a Gaussian, let's say, I don't need to worry about Gaussian, but if it helps you to think about it, think about a Gaussian filter, which is represented by this hand, and I'm moving this all over my domain, right? So at any point, I've centered it at some point R, where R is equal to 0, and I have multiplied this by the velocity field V of x plus R, and I'm going to integrate all over, right? So what this will do essentially will tell me roughly what the velocity field at x is over a length scale L. Is the idea clear to everyone? So if I take a different color of this, so this is my filter, let's say this is my phi. I multiply my phi with all the velocities that I can see in this region. I'm going to integrate it. What sets my, the largeness of this pink circle is set by L. So that's the coarse graining length scale. So I'm going to move this around and I'm going to integrate it with the velocity at every point which lies in this. And after integration, I will get a coarse-grained velocity field because that will be the sum of the velocities at point x, but spread around a region of size L, and I'll get some sort of an average velocity at point x. All right, so this is a level of coarse graining that I have done, performed at scale L. Okay. So in some sense, I can think about VL of x as, yes. Well, I don't need to think about distributions. That's because I can do it on a snapshot, right? So I have, let's say, from some data, I have velocities at this point, this point, this point, this point, this point, this point, this point. All right. Now I've taken this filter, I multiplied it with all of this as the filter vanishes. Then what comes out of this is, let's say, the center I call x. After that multiplication integral, what will come out is in some sense the average velocity that I can see over a length scale L. So I don't, so what this process will do, it's somewhat like a low pass filter that we had used in our second lecture, because this guy is not going to contain any information of what's happening to my field at length scales larger than L that I've used. It is collecting all the information of the field at length scales up to L and nothing beyond. Right. So in some sense, this is like a low pass filter, which is sort of ignoring the contributions of anything larger than L. Yes. Right, exactly. So that's what we'll sort of get to in a second. So maybe I'll address your question first. So first is, of course, there is a slight problem. What you were saying is, so what she was saying is, what happens when I take L small and small? So am I going to the smallest length scale? So mathematically and also physically, I really am somewhat inhibited to take the L going to zero limit here. The reason I'm inhibited to do that is, at the end of the day, once I've applied that, I am looking at the average velocity over my scale L. Now, as I shrink L all the way to zero, I'm really going close to the mean free path of the individual molecules which are making up my fluid, right? And there, my Navier-Stokes description itself doesn't make sense. So what do I mean if I'm going to coarse grain at length scales which are? So I will certainly try and keep L, let's say, above eta, around eta, hovering around eta, or a little above. Thank you. I should have mentioned that. That's precisely what we are going to do. Very good. So in some sense, this will give me my average velocity of a fluid. I was about to use a fluid eddy of size L, but I'll use another favorite word for fluid dynamicist, a fluid blob of size L. Right. You can think about it as those little things that I was drawing when I was doing the cascade picture. So this will give me the corresponding velocity scale. So this, of course, is going to be a low pass filter. And the advantage of that, yes, sir. It will depend how well I define my filter, but this would be some sort of. So if I take a kernel phi, which is nice and smooth and symmetric and everything, this will weigh things out nice. And you're right. But for the manipulations we'll do, for precise calculations, I need to worry about how to define the kernel carefully, right? But for the manipulations that we will do in this course, whatever little remains, we really don't care much about the precise nature of the kernel, as long as some of those properties are nicely with, that is normalizable, that it falls off fast enough, etc. Yeah. It's the integral. So this is, again, we want, I mean, as I satisfied, so all that is saying is that this kernel has a compact support. The fact that it's vanishing, which also comes from the fact that this goes away as R becomes large. Okay. Yes, sir. So let's come to that issue in a minute. It will be a simple average. It will not be something which is a moving filter. So when we actually manipulate that, right now, I really don't need that information, whether it's a step function, a Heaviside function, etc. I just need something which just going to obey it. You'll see why that will become kind of irrelevant. For calculations, again, you have to worry about the, by calculations, I mean real calculations from which you want to get numbers out. You will have to worry about it. Okay, very good. So this guy, as we said, this guy is a low pass filter which contains no information about scales greater than L. So you can construct the inverse, and this is, and what I'll do now is really the most important thing that we need. You can construct the inverse of this as, just take the subtraction I subtract the field from the full field, that will be my inverse. So this is something that we did in the first class when we did the filtering in Fourier space, remember? So this is really in that same spirit. And this, by definition, you can write as the integral I'm just not writing the integral every time. Okay. And the reason you can write this is because this term will not matter. This is a function of R. The integral is over R. So whatever V of X I stick in really doesn't contribute to anything. So I can add, subtract, do as I will. The reason I'm going to do this is because we are always chasing delta V in the last, for this week. And so this allows me to think in terms of delta V. Okay, so I'll make a few remarks. This wasn't there, no, till yesterday. This was? Ah, yes, very important. So let me make a couple of remarks and then I'll let you guys go. All right. I'll pick it up from here and you all can digest a bit of this over lunch. So this is, so what we are doing is using the same spirit of deriving. Now this I put in quotes because at the end of the day, we had already written down the Navier-Stokes equation as a hydrodynamic description, but now I'm going to do a further coarse graining, right? So that's why it's in quotes. And you can think about L as some sort of small scale or gradient scale that you were mentioning, all right? But certainly larger than, let's say, mean free path scales that we are thinking, that one can think of. So this also is a process which is perhaps closer to experiments. That's because in an experiment, when I stick in a hot wire anemometer or whatever I want to stick into my flow, I'm really not measuring the velocity at the geometric point x, right? I'm really measuring, in some sense, the coarse grain velocity over a scale L, which might be, I hope I'm not doing something, which might be over the scale at which my instrumentation is. So this sort of sets up the problem. We'll come back and continue with this problem tomorrow. This sort of sets up the problem of rewriting or redoing the calculation that we did, but now more formally in terms of certain certain inequalities that we are going to derive. Some of them we won't have time to derive, but standard sort of real analysis textbooks. So if you have friends who do mathematics or you do mathematics, you will know exactly what they. So these will not be any more difficult than triangle inequalities or Hölder inequalities that we are going to use. And then we will see, so I can tell you what we will see in case you don't show up tomorrow. What we will see is that we'll have a much sharper constraint on the zeta p exponents for p greater than equal to 3. And we'll see that it all hangs together. So tomorrow will be, so okay, so we are basically done today, but tomorrow is the last lecture. So tomorrow things will get tough because we will also see things in Fourier space, which we sort of neglected after the first couple of lectures. So good luck for tomorrow.